Start. So our last speaker of the day is Benedikt Bünz, who's going to tell us all about recursive proofs. Again, a very important technique that's going to come up again and again throughout the week. All right, Benedikt, the floor is yours.
Thank you very much. Thanks for having me, and thanks for all being here in such large quantities. So we're going to talk about recursive proofs. So what is a recursive proof? So this is basically a one-slide talk. I'll just tell you what it is, and then we're done. Now, there's a lot to talk about. So let's assume we have two SNARK systems. Sometimes they're the same, sometimes not. And a recursive proof refers to sort of these a general class of constructions where the prover proves something about the verification of another proof. So I have some statement and some proof, and I have some language. It's possibly indexed by a verification key. Again, there's slightly different variants. But the key component here is that the prover proves that, or the prover, the P prime here, proves that the verifier V would have accepted the proof. Okay, so it produces a second proof here, pi prime, that basically says I know, and we'll generally consider proofs of knowledge. So it says that I'll know a proof pi such that the verifier V would have accepted on statement X. Okay, and we'll also and the knowledge soundness of pi prime V prime will imply that we can extract pi. Don't worry, we'll talk a lot about sort of extraction. It's a very complicated topic. And the other thing that I want to note is that we generally refer to, I'll talk about something called the recursive circuit. So what happens is that the proof system pi prime is, let's say, a proof system for NP, let's say for arithmetic circuits. So what happens is that the verifier, which is described as an algorithm, I need to do an NP reduction to, let's say, an arithmetic circuit, such that the prover P prime can prove the statement about V. So I have to formulate V as an arithmetic circuit, and for efficiency reasons, we will wonder and care about the size of V as a circuit. Okay? So that's what a recursive proof is. So why would I do this? Why, just for fun, or what are the applications of these recursive proofs? So it turns out there's a lot of them. So sort of the first one that came up in this seminal paper by Valiant was that I want to prove a sequential computation. So I have some state x0, and I want to evolve the state using a transition function f. It might be a non-deterministic computation, so there might be some additional witnesses that are input. And I would like to prove the following statement, that xt is f applied t times to x0 with some non-deterministic witnesses. So how can I do this? Well, one solution is that I take sort of the first 3 lectures and I just apply a SNARK to it. Right? And this sort of works, right? I can produce a SNARK, and by the beautiful, wonderful properties of SNARKs, this proof here will be short and efficient to verify. So what are the downsides of this naive solution? Well, it's not very memory efficient. So I have to actually remember all of the witnesses and all of the intermediate states of the computation in order to produce this proof. Secondly, imagine this is not just some long computation, it's an evolving computation, one that keeps on running. So let's say I've done this for t steps, and now I do one more application of f to the function xt. Well, what happens then? Well, then I need to redo the entire work. An additional step of proving requires reproving everything. Also, additionally, sort of finally, if the prover is superlinear, it's going to be superlinear in t times f. Okay? Is that clear? Yeah.
So I guess the non-memory efficient is not necessarily true, but often is.
Well, I mean, at the very minimum, it seems difficult to imagine that a prover would not have to remember W1 through W
sure, but you're saying that the entire trace of the computation and so on.
Yeah, I have to at least store the trace states. It could be a streaming prover, that's true, where this is the case. So it is, you're right, it is not necessarily true. But at least before, when I start my proving, I have to know or store the entire trace of the computation. And in practice, we oftentimes use proof systems which are not necessarily streaming friendly.
You don't need to store the entire trace if you were doing it.
Yeah, you're right. If I have a streaming, but we oftentimes, you're right. Sure. Yeah. If I do it in
Usually
a
there are
streaming
trade-offs
manner,
to doing that.
yes. But we'll see this is actually a way to construct a streaming-friendly program. Yeah.
Sorry for about this question. So, do you mean that you could simply, but you'd still need access to everything, right? Like you don't have.
Yeah, but I can. What Ron is saying is that while computing F, I could start my streaming-friendly prover. Like I could have a magic prover, and in fact, we'll see, how to construct one using recursive proofs. So it's a bit of a circular thing. But I could have a streaming-friendly prover that ideally, computes F from x0 to x1, and then processes W1 and then erases it. So it only has a small amount of memory to store x0, W1, and x1. So
but at the when we're doing the fourth step, for example, so we still need access to W0. We can only access one at a time, but we need access again, right?
No, not okay. With the streaming prover the answer is no. I can actually start proving while I'm computing.
Without this, okay.
There are constructions of streaming proofs that don't use recursive proofs.
Maybe not streaming proofs, but complexity preserving SNARKs will get you there.
Yeah.
Well, yeah, you're gonna build a streaming
Okay,
proof.
but we're going to build. We'll see how to do this.
Okay,
Okay, so let's go to motivation 2. So motivation 2 is handing off computation. So let's say we have a bunch of friends here. They want to, build an AI model, and they're part of the AISC, and they want to build this AI model by using federated learning, right? So each one of them, does some local computation, contributes to the model. They somehow aggregate it. If you want to think of something simpler, just think of addition. They just want to add their local numbers and shares, and they want to hand off this computation and apply these functions to each other's input in some sort of DAG-style fashion. And let's imagine they're not actually that good of friends, so they don't quite trust each other, and they want to see basically at every point in time. Here, Alice here wants to see that the inputs were actually computed correctly and everybody has done their work correctly. And additionally, maybe someone at the end wants to see that fx7 was computed correctly. So what is the naive solution? Well, one thing we could do is that each party creates a proof and we attach all of the proofs to the computation. The downside of this solution is pretty obvious. It is linear in the number of steps. Okay. So what is the solution to this? So the solution to this is something that we call incrementally verifiable computation. And here the idea is that at each step, we not just involve basically our computation, but we also produce a proof, pi, that basically that the next prover can take as input, and that proof gets updated in the next update of my function. And of course, to make this interesting, and then at the end there's a verifier that takes the final computations, the final output of the computation, and usually also the input of the computation is forwarded along, and the final proof, pi t, and accepts or rejects. And the security properties that we want is completeness. So given a valid proof pi I for xi minus 1, the prover P can generate a new valid proof. This is actually something that's called adversarial completeness. So even if the proof was generated maliciously, we want to be able to continue the computation. That's sort of the strongest form of completeness. Knowledge soundness, which says that given a final proof here, pi t, I can essentially extract the entire trace of the computation. And then finally, this thing would not be interesting if we didn't have the efficiency property. We'll talk a lot about efficiency today, which is that the proof size and the verifier time should be independent of t, and this rules out the solution of just attaching all of the proofs for all of the steps. So I really care about the proof size and the verifier time to be independent of t. It doesn't actually necessarily have to be independent of a single evaluation steps of f, and we'll see that relaxing that is useful. One note is that IVC for P can be built from standard assumptions, from batch arguments. We will today focus on the NP case. And I think there's actually talk later today to also build that from, well, obfuscation and lattices. So I'm very interested in seeing that later in the week. Okay.
Verifier verifies the whole computation, right?
The verifier checks the proof, the final proof, but the knowledge soundness property implies that the whole computation was correct.
But does the verifier know x1 to xt?
No, it just knows x0, xt, and pi t.
And T. Also T?
Also, t usually, it doesn't actually necessarily have to, like, yeah. I mean, yeah. Oftentimes we'll pass x0 along as part of x, sort of the function can kind of pass along whatever information it wants.
Are you going to show an example of application?
Yeah. I mean, one of them is literally these distributed computations. I have a bunch of provers. We all together want to compute the function. But there's more. We'll talk more about that.
My only question is really about if it needs to know the xi's or not.
No.
XR is like intermediate computation. Think of it like it's in the, nobody cares about the intermediate.
Yeah. So no, the verifier will not know, and in fact the efficiency requirement sort of necessitates that it cannot know the intermediate xi. There's a generalization to arbitrary directed acyclic graphs, which is called PCD. Here we actually need sort of an upper bound, so it works for arbitrary graphs, but we do need an upper bound on the arity of the graph. Okay, so how do we construct IVC? After that, I will talk a little bit more about applications. But yeah, how do we construct IVC from the recursive composition of SNARKs? So assume I have my function f here, I evaluate xt, and I get xt plus 1. And let's say I have some old proof pi t floating around. We'll see where it comes from. And so what I have is also I can write down the verifier for my SNARK. Let's call it v, which takes as input xt and pi t and outputs either 0 or 1. So this is a SNARK verifier. And what I will do then is I will build a recursive circuit. So I will build a circuit that both evaluates f. So it checks that f on xt is actually equal to xt plus 1. And it checks that the verifier would have accepted on inputs xt and pi t. So I build this recursive circuit. So I do this NP reduction. And then I use my SNARK prover, which is a prover for NP statements, for arithmetic circuits, to then create a proof, pi t plus 1, that this statement was correct. So essentially, at a higher level, the prover proves that the previous step of the computation was correct and that the previous SNARK was correct. Okay? And this basically gives me the IVC prover. So this is the IVC prover. And the IVC verifier simply runs the SNARK verifier. So it takes the final proof and then runs the SNARK verifier. Again, usually x1 is going to be part of xt, actually. So I run the SNARK verifier on the final step. And if the SNARK verifier accepts, the IVC verifier will also accept. Okay, so I'll talk about completeness. So completeness follows from SNARK completeness. And soundness, basically, we want to recursively extract the transcript using the SNARK knowledge soundness. This is not all I'm going to say to it. It's actually quite complicated. There's a lot of issues with that. So we'll discuss them in a minute. For efficiency, so the size of, the efficiency requirement was that it's independent of the size of the computation. And if we think about it, what do we get here? Well, we get one SNARK proof, right? The IVC proof essentially is one SNARK proof plus, a little bit extra for the state of the computation. So it's one size, one SNARK proof for R. Okay, there's, yeah?
Kind of circularity here. You're saying that, I want SNARK for this relation. Mm-hmm. The relation depends on V, mm-hmm. But then you said V to be the verifier for the SNARK itself.
Yes.
So is this V the same for all the steps, or it changes every step as its own?
No, it is yes, it is very confusing, but that is exactly the case. So what we assume is that we have some I think the simplest way to think about it is that if you assume the SNARK verifier was somehow universal, right, then it would make sense. No, maybe not.
There is still a circularity, I think.
So there is a circularity, and sort of, for example, one really, really important requirement is, you might wonder, okay, does the circuit grow each step? For example, does the circuit grow each step? So we have SNARKs where the SNARK, for example, is constant size. So, for example, some built on the KZG commitment, that Pratyush talked about. The SNARK verifier is actually constant size. It just does a pairing. It takes as input some verification key and the statement, and then it does a pairing, and that's all it is. And it turns out that then I can upper bound the size of the circuit R, and I can actually implement the SNARK verifier here. It's actually more general. As long as the SNARK verifier is sublinear in the statement that is proven, then I can upper bound the size of the circuit R. I'm not sure if that helped. Or
I think the thing to note is that the verifier can take in a digest of R. It does not hard code any information about R beyond the size. Yeah.
So the verifier needs to be sublinear in R, which already necessitates that it cannot read R. So the way that we do that is we use a pre-processing SNARK, where the circuit itself is, sorry, thank you very much, Pratyush, that's a great comment, where the circuit itself is sort of pre-processed in a verification key. This verification key is succinct and gets fed as input to the recursive circuit. Okay? But yes, it is it is a bit confusing. Any other questions? Yeah.
Oh, no.
No? Okay. Good. You sure? Okay, then let's continue. Okay, so I want to talk about some more, now that we sort of understand IVC PCD, there's actually some other applications of SNARKs. Some of them use PCD. So for example, there's these things called property preserving SNARKs. So let's assume I have a SNARK which isn't that great. It has a bunch of bad properties. It has large memory requirements, a large CRS, a sort of large verifier. We always assume the verifier is sublinear, but let's say it's like not as good as it could be. But it has a fast sequential prover. So it turns out what I can do is I can transform it then into a SNARK A prime that is great. So it has a fast parallel prover, some constant memory, constant CRS, constant size verifier. So how do I do that? Well, essentially what I will do is I will break up my function. Let's say I want to build a SNARK A for some function f into t uniform steps of f prime, where each of them is roughly is f broken down divided by t. Okay, so f prime now can be constant size, and so now I'm applying a prime to something that is constant size. So the memory, the CRS, and the verifier are naturally constant size. Okay. And also I can do this in parallel by basically building a PCD tree. If I basically do this in a tree, then I can do the proving in a parallel manner. So the parallelism memory verifier is for f prime, which is constant size, plus the circuit of VA. Okay. So there is this overhead. We also call this recursive overhead, which is that I need to basically now prove the circuit VA. So I want to keep that as small as possible. Yeah.
But here you have to assume that f is somehow can be broken into sequential steps. If it's a crazy circuit where wires go all over the place, and you cannot break it into sequential state compositions, and
so this is why I said it's a uniform step. So that is correct. So, but I could, for example, build a circuit for a virtual machine that then executes f in some manner, right? And I have, like, for example, I can commit to the instruction set. I can pre-process what kind of instructions I want to execute in order to simulate f on my virtual machine.
But if the virtual machine does random access into huge memory all over the place, and you
I might need to do memory checking, and like there's an overhead to making it uniform, but it is possible.
And it's done in practice nowadays.
And it is done in practice. This is the company that Ron works for does this. So yeah.
Even when the memory is not
Even when the memory is not bounded?
you have tricks like to deal with it?
You mean the memory in the computation that is run?
No, like the way you draw F, I would think about it as a bounded memory computation, right? You always have a small configuration.
Yeah, I don't know if when the memory is unbound. I would need to think about that. I think more about bounded cases, but yeah, I don't know.
And usually the size of the proof is like the size of the memory, right? That's
No. You can use memory checking to reduce it.
maybe that's
We can maybe take that offline. That's a bit more in the weeds. Okay, so yeah. Whoops, sorry. The second application, the fourth application and final is SNARK composition. So this actually is, let's say I have two SNARKs. So we saw, again in Produce talk, where we had this discussion about, in practice, people use these hash-based provers because they're very, very fast, but they have sort of a slow verifier and the large proofs, again in apostrophes because it's concretely slow, asymptotically it's still succinct. And then I have a second SNARK which sort of has the opposite properties. It's something like curve-based, which has really, really small proofs and fast verifiers, but a slow prover. And it turns out that recursion allows me to combine this to get a SNARK C, which has sort of the best of both worlds. So how does this happen? Well, the solution is very direct. We just simply use SNARK B to prove the correctness of SNARK A. And by the way, this is done like in practice all the time. Like they do this all the time in all the industry applications. Why do they do this? Well, mainly because, let's say, the final proof gets posted on some smart contract. I want the smart contract cost to be as low as possible. So this isn't just a theoretical sort of idea. This is very much being used in practice. And there's many, many more applications. I won't go into all of them, but there's really nice sort of applications. I can tell you about them later. And this is really kind of the favorite toy of the AISCs. Really loves these recursive proofs. They're used all the time. Any company really that is building large-scale proofs uses some form of recursion. And this is why it's so vital to understand their security and to improve the constructions and get better efficiency. Okay? So wait, any questions up to now?
using the proofs and IVCs. Like, it's the only way to get IVC.
Wait until the end of the talk. So yeah.
What is this company?
Oh, I don't know. I guess something got lost in the process. Could be yours, So let's talk about the security. So there are unfortunately multiple security issues, or fortunately, if you're looking for problems to work on. And one of the main one is this arithmetization of V, right? I need to put V into the circuit, and I need to arithmetize this. But as we heard, this morning, a lot of I need to arithmetize V, which means that I really need to instantiate it. I need to write it down as an algorithm. I cannot write down. I don't know how to write down an oracle as an algorithm, right? So V can't contain any oracles. But we said we construct these things we said we construct these things oftentimes from SNARKs, and essentially all the SNARKs that are used in practice, or almost all of them, will contain, are built, or the security is proven in some form of random oracle. So for example, they use some Fiat-Shamir heuristic, or it's, the knowledge soundness analysis is done using random oracles. So what we do is this massive security jump. So we assume, we have some PV, which is secure in the random oracle, and we then, I don't know why this was flipped, but yeah, we then assume that if we replace PV with, let's say, Fiat-Shamir, although not actually Fiat-Shamir, like some arithmetization-friendly hash function, then we are still secure. Okay, so this is the big, big security jump. And what are the problems? There are a couple of problems with the security jump. First of all, it's just not true, right? We have constructions of SNARKs since '98, where we know that there are protocols that are secure in the random oracle model that cannot be secure if they're instantiated with any hash functions. And sort of this has gotten much more interest again recently because we've sort of had a paper by Ron and others showing that even GKR, sort of a widely used protocol, can be insecure if you do this transformation. Okay, so this was for the first time. These attacks here are a little bit more contrived. They kind of embed a trapdoor, versus this is an attack on basically GKR applied to specific circuits, and it's in particular worrying because it only applies to GKR on specific circuits, but it's exactly the type of circuits that we do need in recursion. It is essentially circuits that evaluate the Fiat-Shamir hash, which is exactly what we do in this recursive circuit. We evaluate the entire verifier, which includes obviously the Fiat-Shamir hash. Okay, so yeah, recursion relies on this ability. So what can we do about this? So there are a couple attempts to basically better understand and analyze the security. Yeah.
Hey, sorry. On the previous slide, you just said you mentioned arithmetically friendly hash functions. What did you
Oh, it's just basically as I said.
Can you please repeat the question?
Oh, I mentioned these arithmetization-friendly hash functions. So it turns out, right, again, as I said, we care about the size of this recursive circuit. And it turns out that some hash functions, like SHA-256, for example, if I write it as an arithmetic circuit over a large field, it will require about 30,000 gates or 20,000 gates. But now people have designed hash functions, much more modern hash functions, which take much fewer gates to arithmetize. So they're in their constructions, versus SHA-256 is designed to be run on x86, on an x86 processor. There's things like Poseidon, which is designed to basically be evaluated by an arithmetic circuit. One security issue that I didn't talk about, but which is also really important, is to understand the security of these hash functions, because these are much more modern, and again, a lot of security relies on them. Okay.
I'm not sure I understand Fiat-Shamir. So Fiat-Shamir is a transformation from an interactive protocol to a non-interactive one. Where is the interaction? There was no interactive.
So sorry, I use Fiat-Shamir differently here. I mean, just replacing the random oracle with a it's like the Fiat-Shamir heuristic. It's replacing the random oracle model with a cryptographic hash function. That's all I mean with this. Okay, so one thing that would be better to analyze the security of these SNARKs would be if we could build a SNARK in the random oracle model that proves statements about the random oracle model. Because then we could at least build the entire PCD construction in the random oracle model, and only at the very end we would have to make this jump. Okay, instead of having to first make this jump and then build another SNARK in the random oracle model. Well, unfortunately, this attempt won't work. It's been shown by Z and Ale that this is impossible. Okay, so we just know this won't exist in the random oracle. So that's a little bit sad. The other idea, or the other attempt that people have tried, is to extend the random oracle model to enable an end-to-end analysis of PCD. So there have been some earlier attempts. Unfortunately, they are not, we have no idea how to then heuristically even instantiate them, other than using secure hardware, which kind of defeats the whole purpose. Then sort of the most recent work is something called the arithmetized random oracle model, which I actually don't want to really go into the details of it. But the AROM, it suffices to build PCD. But one downside of it is that the attacks that apply sort of these Fiat-Shamir style attacks. So for example, the GKR, even applied to relativized statements, is still secure in the AROM. But we know it is not secure in the real world. Okay? So that's one downside here that would be great to solve. And I feel like this is an open problem, although there's some work that we'll hear about later this week, which is to build a model that is sufficient to capture these style of attacks, but enable an end-to-end PCD construction. And there's some candidates by Zandri and one that we'll hear about later this week. But today they mostly try to specifically evade the attacks or the capture the attacks that we've seen. I'm somewhat confident that this is not the end of the line, and we'll see more really interesting work there. But it's a really important area.
Either way is going to be the random walk model. You're not getting any, away from the random walk model. You're just applying the random walk once instead of several times to itself or something.
So there is a talk. I mean, this is obviously okay. I'll have my open problems section later. Obviously, the best thing would be to build a PCD secure in the standard model, right? And I think there is a talk later that builds it later this week. That builds it from obfuscation, which I'm very interested to hear about. So that's the first start, and then it's about lowering the assumptions. But yeah, I think all the practical constructions are in the random oracle model. Everything that we know. So
we don't know whether PCD exists in the random oracle model, right? By not the heuristic assumption.
I mean, in fact, we kind of know that it doesn't exist in the random oracle model because this is this BCG 24 paper. I'm not sure if it exactly implies that, but
exists the random model exists in the random oracle model too, right?
Yeah, I guess that's
No,
true.
but with
Yes.
other assumptions.
Yeah, that's true.
But trying to go to your question, like the current situation is you're assuming the adversary only uses the hash as a random oracle, but the construction itself is using it not as an oracle. So if you could do it end to end, at least you could say nobody is using it.
Right. Yeah, that's a good way to put it. Yeah.
So earlier in the way you showed how to supposedly construct it from SNARKs, the fact, the entire problem is that the SNARK is using the Fiat-Schumacher transform, right? Like if the SNARK would have not used the Fiat-Schumacher transform, then the recursive construction would be totally secure, or at least as secure as the SNARK.
Yeah, then at least we would have an end-to-end construction that's secure in, let's say, the random oracle model.
Yeah.
It's exactly like I think Ron said it well, like that. Normally we assume the adversary only uses the hash function as a random oracle, but here we actually explicitly have the construction itself uses the hash function not as a random oracle but as a concrete instantiation, because otherwise we couldn't build the
good guys more power than the bad guys, which is
yeah. Okay. I want to move on to there's a second set of security issues, which is about extraction. So the IVC extractor, so how do I extract? Well, so the IVC extractor will call the SNARK extractor on the output to extract PT-1, XT-1, and WT-1. Okay, so first step is easy. But then how do I continue, right? I would like to then extract from, maybe this prover here, but this prover doesn't exist yet. So what needs to happen is that in order to extract from an internal step, SNARK, I need to simulate a prover pi tilde for that SNARK. Okay? So how do I simulate the prover? Well, I need to be able to construct proofs for this step. And the idea is that, again, I basically generate those proofs by invoking the extractor for the outer SNARK. Okay? The key takeaway, if this is a bit too complicated, don't worry about it. There is a key problem here, which is that each extractor can invoke this simulated prover up to polylambda times. Okay. Well, what happens now? Let's say I'm talking about the simulated prover here. I'm invoking the extractor polylambda times, which talks to a simulated prover here, which invokes it polylambda times. I get an exponential explosion. Okay. So the runtime of the extractor is going to be exponential in the depth of the computation, which means that the depth must be constant in the security parameter. Well, that's insane, right? Like all these applications that I talked about, I told you, of this magic land where I could, prove 1 billion steps of computation in a row. Well, billion, okay, maybe that's a constant, but it's not a constant in the security parameter, right? So how do I deal with this? Well, there are two ways to deal with this. So there's first, it's constant depth IVC PCD only, and even with constant depth, there's a major security loss if I were to actually account for this, right? I would have to set my security parameter to be massive to do this. So the old solution is to decrease the depth. So how do I do that? Well, essentially, I use something called tree-based IVC, where I can build a tree which has logarithmic depth, and I can even make it constant depth if I increase the arity. But still, this would have a really, really high security loss. There's also the practitioner's solution, which is to do absolutely nothing about it. Right? And we just assume that basically the security error of the IVC is the same as the soundness error of the SNARK. And this is, it's not quite as crazy as you think, because there is absolutely no matching attack. Right? I think this would be also a really beautiful paper to sort of, get even some completely contrived scheme that would exploit sort of the depth of the scheme and would exploit this gap. Okay? But we don't really have, I don't think we even have contrived examples of this, but it's really interesting. There is fortunately a saving grace, which we've already talked about, which is straight line extraction. So Pratyush was wondering whether for your application we need straight line extraction. Well, in this application, we definitely need it if you want to consider security. And the reason is that if we assume that the SNARK has straight line extraction, won't go over the definition again, essentially then we don't get the exponential blowup. And in fact, we even get, this was recently improved, to say that the soundness error of the PCD is the same as the one of the SNARKs. It's not even linear in the depth anymore, which is great and which sort of justifies the parameter choices that have been done by practitioners. However, again, there's two problems with it. We're only able to construct, again, straight line extractions in these idealized models. I don't think one can even really think about straight line extraction in these standard models. Maybe, yeah, if you encrypt something, but we just have to assume that this holds for the real world instantiations. And the second problem is that some SNARKs of interest don't have straight line extractors. So for example, up till recently, this was true for SNARKs from non-efficiently decodable codes. We've recently done some work that William will talk about that helps with that. But also, there's other families of SNARKs. So, sort of, this is to motivate, basically prove your SNARK constructions to have straight line extraction, even in an idealized model, because it really matters not just for composability, but it also matters, well, I guess this is a form of composability, but it also very much matters for these recursive constructions. And if you build a SNARK, someone will use it recursively. Okay. I'll sort of, before I go to the second part of the talk, I want to mention some open problem. There's one obvious one is to build IVC PCD in the standard model. I talked about this model that captures these Fiat-Shamir attacks. Again, there's been some work on this, but then these contrived attacks, straight line extraction, and yeah, maybe closing the gap between what it means to have straight line extraction in an idealized model and what it means in for a transformed protocol would also be incredibly interesting. Any questions on security?
Is it possible even to build IVC that achieve knowledge extraction in the standard model? Like if you want to have knowledge soundness, is it possible to have it in standard model?
Yeah, I mean, I guess it would be maybe some sort of recursive model, or maybe it encrypts. Yeah, I guess.
Of knowledge, you can't.
So it won't be knowledge sound.
Yeah, probably not. Yeah, probably, yeah, that's right. Good point. Okay. So, I want to talk a little bit more about efficiency and sort of what the concerns are. I showed you a construction already. So why do I even have to talk about efficiency? Well, if we look at this construction, sort of this is a high-level overview, right? I said we implement this verifier arc, and we have this recursive overhead. So, so the concrete issues are that the size of this verifier arc is practically large. So, for example, let's say I use a pairing-based SNARK, then this might take like 1 million gates. I think nowadays it's maybe people have done more arithmetization tricks to get this down a bit, but it still takes hundreds of thousands of gates to basically build a circuit that computes a pairing. Okay, and And also, it's riddled, sort of another issue from a security point of view. The more complex these circuits are, the easier it is to mess them up, right? And that, again, directly leads to a security issue. Sort of like making the compilation correct. Okay, so the other issue is that I'm running the SNARK prover, so whatever constant overheads my SNARK prover has, my IVC prover will have as well, right? It is, if the SNARK prover is 1,000 times slower than evaluating F, then the IVC prover will also be 1,000 times slower than evaluating F, at least. Okay. So to see another reason to motivate why basically this recursive overhead is a bottleneck, let's go back to this application here. And if we see here, right, the memory CRS and the verifier for is this F prime plus the circuit VA. So one question that you might wonder is, how do I set T? Okay, let's say it's some nice uniform computation where I don't even have to worry about making it uniform. But how do I set T? Well, I kind of would like to set T to be as large as possible, right? Because my parallelism improves with T, my memory gets smaller with T, my CRS gets smaller with T, my verifier gets more efficient. However, it is basically lower bounded. If I make it too small, it is lower bounded by the circuit size. So the smaller I can make the circuit, the larger I can make T, the smaller I can make F prime, and basically the better this application becomes. And this is kind of true for most of the applications. So it is not just the constant. Sometimes, when you tell theoreticians it's just the constant, they get uninterested. But it really matters in applications because it becomes the bottleneck. Okay. The SNARK prover is also the bottleneck, essentially because of the constant overheads, and many of them have strong assumptions. So, but yeah, so this leads to sort of natural questions. Are SNARKs actually necessary to build IVC PCD? It's so natural that someone, I think, asked it earlier. So the answer is for P, we already know that this is not the case. But it turns out that it is also not the case for NP. And in particular because of something called accumulation schemes. So what is an accumulation scheme? I'll give a speed run review of SNARKs in order to compare them to accumulation scheme. So in a SNARK, I have a prover that produces a proof, and the proof is much smaller than the witness, and the verifier is much more efficient than the size of the witness of the statement. Okay, so it turns out that there's something simpler which also suffices to build IVC, which is called a reduction of knowledge. So let's assume, again, I have some instance witness pair which is in some relation, and then I have a prover and verifier which takes as input an instance and a witness, and the verifier only gets the instance. And then what we'll do is we'll have some sort of non-interactive reduction. Sometimes we'll write it, we'll talk about the interactive reduction, which we then compile to be non-interactive using Fiat-Shamir. But let's think about a non-interactive reduction where the prover sends a proof pi, and then the verifier outputs x prime, and the prover outputs w prime, such that x prime, w prime are in some different relation. Okay? So this, is something very, very generic, right? But we can define completeness and soundness in the natural ways for it. But it turns out that this suffices to build something called accumulation scheme.
Where are you talking about size?
I haven't yet. I don't have any efficiency requirement. Actually, the efficiency requirement will be in particular that this proof here itself will be short, will be efficient.
And you want x prime will be short.
And x prime and the proof will be short, but importantly, the witness itself can be very large. Okay, because it's large here and can be large here because the verifier never has to see it and touch it. Okay. Yeah.
The proof pi is not even in this
You want to say if you succeed in cheating.
Like if the verifier accepts the proof, then
Yeah. Sorry, this is a very high level. Of course, yes. Okay, so an accumulation scheme is something of the following form, where I start with two relations, so R and R star, and then it's a reduction of knowledge to R star again. So basically, I go from R star to R and star, and I can fold in a new thing of R. So I can accumulate, sometimes it's called accumulation or fold in. I can accumulate basically validity of R with, you know, this validity of R star. And sort of the pictorial way to see this is, you know, I have a bunch of things which are in R. These are later on going to be the actual statements that I'm trying to prove. And then I'm going to fold them into this, or put them into this accumulator R star, such that at the end I'm left with one R star that I have to check validity for. Okay? So in general, so more precisely, this is also called split accumulation or folding schemes. And we can, of course, extend this to, you know, make it R to the n and R star to the m. But we'll focus on this sort of binary case first. Okay, so why is this interesting and why is this necessary? Well, it turns out it's going to be weaker than an argument for R, and we'll see an example sort of that illustrates this. So an argument for, let's say I have, you know, an argument for NP, then of course I can construct this because I can, you know, this is essentially what IVC, sort of IVC from SNARKs does. I can prove R would be the function f that I'm evaluating here, and R star would be the validity of the previous proof, right? And then I can construct a new proof that basically says the function f was evaluated correctly and R star was evaluated correctly. So arguments or SNARKs suffice to build this, but it turns out that we can build this in a simpler way. Okay? And we can also build IVC from it. So to see that, we'll see that basically, we'll see that basically the idea is going to be, I'm going to skip a little bit forward, that I'm going to basically put this accumulation verifier inside of my recursive circuit. All the details don't matter quite as much, but I'm going to put this accumulation verifier inside of the recursive circuit. So I'm going to prove that I did the accumulation correctly, and I'll have on the outside of the circuit, I have this additional accumulation prover which takes the previous witnesses and computes the new witness. So the big difference here is that I'm doing previously in the SNARK construction of IVC, I just fed in the proof directly into the recursive circuit. Here, I have this additional information which sort of gets passed outside of the recursive circuit and reduces which the accumulation verifier produces. And in order to do that, it basically supplies the accumulation verifier with a short proof that it did the job correctly. Okay? So this additional power here is going to make our construction simpler. And what is the relation R that I'm proving? Well, the relation R is going to exactly check that the function was evaluated. It's exactly this recursive relation. So it checks basically, or it's a type of proof for, let me say this again. What is R? Well, R essentially is a proof that this recursive circuit and f were evaluated correctly. So, okay, wait, I'm using a proof again. So what has changed? Well, the big difference that has changed is that I have this R here now, and I have a prover that outputs, you know, x comma w, essentially a proof for R. But now the verifier is nowhere, like the verifier for the proof is nowhere to be seen. It's not inside of the circuit. The verifier for the NARK, in fact, is quite trivial. It simply checks that x comma w is in the relation. So what this means is I don't need to design a SNARK. I don't need to have any succinctness requirements on the SNARK itself. I can design a NARK, a non-interactive argument of knowledge, that has no additional succinctness requirements. So for example, the witness itself can be as large as the statement, or could be even quadratic in the size of the statement. It doesn't really matter. Why? Well, because I don't have this requirement that the NARK is inside the circuit. The only thing that gets inside the circuit is this accumulation verifier. Yeah, there was a bullet there that we do need knowledge soundness, yes. Okay. So what does the verifier run? Well, the verifier basically receives one instance for R and one instance for R star and checks that both of them are inside the relation. Importantly, the IVC verifier now receives the witnesses as well in order to check the relation. So the verifier, if we make this witness a little bit larger, the IVC verifier will be large. But if we think about our canonical application where I do a million steps of computation, I only run the IVC verifier at the very end. I only run it once.
This notion does not imply SNARK. This template does.
I'm going to talk about this in a second. So why do I want to accumulate? So I want to accumulate, so if I compare IVC from succinct arguments and IVC from accumulation, here this is sort of maybe a better overview. Well, it turns out, so what's the difference? Why do I care about this? Well, it turns out that the prover, pi-ac plus pi-narc, which I need to run here, can be more efficient than pi-arc. And it turns out that v-ac can be smaller than v-arc. This is why, and sometimes it can be smaller from simpler assumptions. Or for the same assumptions, it's more efficient. Okay, this is why I want to accumulate. So going back to your question, accumulation and SNARKs. So accumulation is simpler than SNARKs. We can construct it in settings and with efficiencies that don't admit SNARKs. However, accumulation suffices to build IVC PCD. And IVC PCD enables building SNARKs, right? I can set f to be the step function of a VM. So what gives, right? Like, well, how does this compute? Well, I think essentially one of the jumps, the reasons is that I think there's two reasons actually. So first of all known interesting accumulation schemes require random oracle. So in order to build IVC PCD, we need accumulation in the standard jump model. So there is this jump.
What's an uninteresting?
Well, a SNARK gives you an accumulation scheme. So
It also needs a random oracle.
it also, yeah. Well, there's SNARKs without random oracles. Yeah, but I need a non-interactive one to build to get to this pipeline. I need non-interactive. The other reason is that recursion itself can help improve the properties of SNARKs, right? I can, as I said, I can build a constant verifier SNARK by using recursion. So we know already that recursion can help with efficiencies. So that is to some degree not surprising. But it is still really nice to see that there is this simpler primitive which then at the end of the pipeline still gives a SNARK. And in fact, people are using it to build SNARKs. Okay? So for the last, I'll give a very high-level overview of how these accumulation schemes work. I'll just do one slide. Yeah, okay. I'll do this one slide, and then maybe we'll yeah. So let's say I have a really, really simple statement. Let's say I have only additions. Okay. So I want to check that A, B, and C are triplets. Addition triplets. Okay. Addition itself is not interesting. We'll go to multiplication in 1 second. But let's start here. Okay, and so what is my NARK prover? My NARK prover is basically the simplest possible thing. It outputs x comma w, where w is literally just ABC, okay? And x is going to be a commitment to ABC. So the relation just checks that a plus b minus c is equal to 0, and that the commitment is well-formed. That's it, okay? So I told you I can build NARK verifiers that are simpler than SNARKs. This certainly looks somewhat simple. And it turns out I need this commitment to be homomorphic, but I can build that from discrete logarithms, so something like a Pedersen or a Pedersen commitment. Okay? And the interesting thing is that let's say I have two of these things, so xw and x prime w prime. Well, it turns out that then this whole statement, this whole relation is linear, right? If xw is in R and x prime comma w prime is in R, then any linear combination, any linear function for them is also going to be in R. So this lets me build an accumulation scheme where the verifier simply samples a random challenge f, alpha and f, and then I set my new statement x prime prime w prime prime to be the random linear combination of x, w. And it turns out that if x prime prime w prime prime is in R, then with high probability, xw and x prime w prime are also going to be in R squared.
When you were talking about the accumulation, you were mentioning two relations. What's the other relation here?
So right now, the two relations are the same. It's R and R. We'll see in a second, where they're different. Okay, but right now I'm going from r squared to r.
You just have two statements and making them one.
Yeah. Okay. So obviously I care about non-interactive reductions, so I'm going to, but I can make this non-interactive through fiat chemie. Okay. So this is for addition. You might say, well, okay, obviously this is linear. Addition is very linear. So what about multiplication? So why did I say addition and multiplication? Well, because an arithmetic circuit just says addition and multiplication. It turns out if I can solve those two problems, that's it. I can build accumulation for NP, and that's really all I need. Okay, so for multiplication, it's slightly more difficult. So I kind of have the same setup, only here that I'm checking that A times B minus C is equal to 0. And it now turns out that, I didn't draw the arrow, but if I now draw a line through xw and x prime w prime, that is not going to be an R anymore. Okay, so this is not, you can. But it turns out that if I, draw this line, if I look at it carefully, what I basically get is I get a polynomial, I get a degree 2 polynomial that comes out of here. And essentially, if I can look at the coefficients, the 0 coefficient is going to contain C, the y squared coefficient is going to contain C prime, and then there's this middle coefficient which contains some sort of cross terms. And it turns out that this identity is enough to build a very simple scheme where the prover will simply send CT, or a homomorphic commitment to CT. The verifier will send a challenge, alpha, and then I'm going to reduce it to a new statement where, x prime prime is again the random linear combination of these two things, and w prime prime as well. But I additionally attach this CT here. So now I have x prime prime, w prime prime, which is in a new relation, where basically the new relation states that A times B minus C is equal to this cross term. Okay? So the details don't really matter, but basically what happened here is that I've reduced r squared, to this new relation r star, which looks similar, like slightly different. So it turns out that, I have this reduction from r squared to r star. It turns out that I can do something very, very similar for r and r star to r star. Okay? And this essentially suffices to build accumulation for NP. That's all I need to then build IVC from it. Okay, so let's take stock. Why did we do all of this? Why was this interesting? Well, because the only cryptography really that I needed here was this homomorphic vector commitment and fiat chemie. So there were no PCPs, no polynomial commitments, no trusted setup. It's just a single commitment, to this witness value. So it's extremely efficient, and it's from extremely minimal assumptions. Additionally, if I look closely at the accumulation verifier, the accumulation verifier only does essentially two group scalar multiplications. So if I use a discrete log, it does in order to basically check the homomorphism. So this is also extremely efficient, and in practice much more efficient than, for example, checking a SNARK, which is what would be needed for checking sort of, let's say, a KZG-based SNARK. So, okay. So, so the key benefit is, right, like the key benefit from a practitioner's point of view are these 3 points, right? This is something that we cannot get from SNARKs. I can build, a SNARK with no trusted setup, and a single commitment, and 2 group scalar multiplications. And this is something that basically we don't know how to build from SNARKs, and this is therefore practically very interesting. There's a ton of work in this area. I'll do 2 more slides. I want to say one thing about post-quantum accumulation, which is essentially sort of post-quantum accumulation verifiers need to check this homomorphism, and in order to build this homomorphic vector commitment, we rely on the discrete logarithm assumption. So one interesting challenge is to build this from post-quantum assumptions. And we'll actually have 2 talks later, I think tomorrow, 2 days. Thursday, sorry. Thursday on basically doing this. So we have one variant from lattices, and then one variant from, let me skip forward, from hash-based schemes. that from hash-based schemes that Binny and William will talk about and tell you how these things work in details. Okay, so for example, from hash-based schemes, we can also get something that we can't get so far we don't know how to get from SNARKs. So we can get accumulation from any linear code with essentially optimal parameters. And yeah, we don't know how to do sort of the same efficiency parameters for the same thing for SNARKs. And one interesting thing is that we were able to prove straight line extraction without efficient decoding. Okay, I'll have my final slide on constructions, and then I'll let you guys go to the happy hour, or you can ask questions. So there's a bunch of open questions for constructions. So for example, can we build linear time accumulation for small fields? So right now we have it only for exponentially sized fields. Essentially all the open questions are going to be things that are interesting for SNARKs, but I really encourage people to first look at accumulation schemes because it's simpler, right? So why not? And if we can't, if we can't have it there, then maybe we can extend it to SNARKs, or we can go through the IVC PCD pipeline, a linear time accumulation from lattices. Accumulation without random oracles is obviously incredibly interesting. Right now, we don't have that. Smaller accumulator size, okay, so recursive proofs are incredibly powerful and can be built from simple assumptions with some security gaps. Thank you very much.
Since we're a little bit over time, maybe we'll go to the reception and do discussions and questions at the reception.
Sure.
So let's do that.
Thank you.
Thank you, everyone.